continuous. The second thing I intend to cover is microprogram state machine based design. Okay, there's also something very interesting, that whenever we are designing a system like this, so it's a system. Usually, if it's a real-time system, you have some data which is coming from outside. It may be videos, images, voice, right? And you have these analog to digital converters converting and feeding it to the data path. And if it is a real-time system, you got to make sure that you can process these frames, like say 60 frames of high definition coming into your system. You got to process them in real time. That will tell you that how much budget you have to do the processing, because you cannot just lose data. So it comes to the data path, and then sometimes you have to play that back also. Okay, if you're doing object recognitions, for example, so you have to play that back to a DAC converter. And usually there is a controller which is controlling the data path to do this, And that's something we said almost every digital design will have these two parts, a controller and a data path. If it is not a dedicated, which will hardly you will design a dedicated architecture. Mostly, if it is parallel processing, again, you have to replicate the same algorithm many times for the, okay? For to do the parallel processing. As somebody asked a question, though my sampling rate is very high, okay, but my clock rate is slower. It means that you have to now replicate that logic multiple times to ensure that you can process that high throughput data. So the controller is going to be an important part of your design, the controller. Okay, so so usually we said every digital design would have a controller, which is the intelligent part, and the data path, which is the dumb part, but which actually does the work. So this is the data path. This is the smarter part. Usually it also gets an input. It also sometimes, whatever processing you are making, the status has to go to the control unit to find out if, let's say, you are dividing 0 divided by 0 or something. So it has to take notice of what is happening in the data path, and then it has to change its strategy or change its path of controlling the data path. But all the time, it is just sending the control signals to the data path, and the data path is giving an output. Sometimes also it just generates status, so that the person who is using this would know that in which state your architecture design is. And then we said controller is a state machine controller would always be in this form. Okay, it will have a register which will have the state of this circuit, state of your design at any instant in time. A combinational logic which has input based on the current state, and the input it would decide that what data path should do next. So that is going as an output to the data path. Okay, it is controlling your data path, and then also it will transition into the next state, that now the circuit is in this state, now circuit is in this state. So every state machine based design, the most important piece of information is the state register, which has the current state of the circuit. Okay? In a programmable computer or processor, this is called the program counter, which has the address of the instruction which it is going to execute. Okay, so there is only one program counter register, which is called program counter PC, program counter register, because it's also a state machine. So, but it is running a program where you want computer to do this, to do this, to do this, to do this, to do this. So all these instructions. So every the program split into executable code instructions to the data path to do this, now this, now this, now this, right? So this is important, and this logic would decide based on the input and the current state that what your data path should do. Okay, this combinational logic will decide that what it should do next, what it should do next. So every state machine has this two part. Interestingly, a programmable computer like Pentium, this state register becomes the program counter register, and this combinational logic becomes your program memory, because it has precisely what your uh, data path is going to do. And here is the instruction which will go. Then there is a stages where your Pentium processor would figure out, do the instruction decoding, operand fetching, execution, write back. So it's going to do a lot of things based on what it is told to do, which is in the program memory. And how would you know what is to be done? It is based on the program counter, which has the address of the instruction. Sometimes there may be an interrupt. So if there is an interrupt, that is an input to the state machine, then it will change its course of action, will go and process the interrupt service routine. Right? And so same is the case with whether it is milli or more state machine. We said in this case you have just this logic is what is the control signals that are to be sent to the data path purely depends upon the state register. So it is not considering the input, and the next state would only decide about the next state, and then the next state would decide what the processor is supposed to do. So obviously, apparently there are two memories. One memory is this, the other memory is this. Okay? So the two set of memories, the combinational cloud, which would decide what the processor should do. So we have already covered like ACM, maybe state diagram you can represent on an algorithmic state machine. They put a milli machine and a Moore machine. But this is something which we did not cover, microprogram state machine. What is a microprogram state machine? It is simply all the control logic that you design using if-else statement can be converted into a program and can be stored in a memory. So it's very simple concept that, and what is the benefit of doing this? Because it is becoming a program, you can change the program. You don't really need to worry too much about going into the Verilog code and changing the Verilog code if-else statement. You just go change the contents of the memory, and now there is a new program, and then you execute a new program like any programmable machine. Why you make a programmable machine? Because it gives you programmability. Okay, so as a matter of fact, any state machine can be converted into a microprogram state machine by converting all the control logic into a program and the state register into the program counter register. Okay, that's simple it is. Okay, so you have a state register which goes this as an address to the memory, program memory, and if there are inputs that are also going to decide that where your program should jump, so they also become part of the input, part of the address bus. So this address would be now two parts. One is part which is governed by the what is there in the state register, and another part which basically is the bits, the inputs that are coming in. So your address is now split into two parts, an input and what is there in the state register, and data path is also split into two parts. This is the part which is controlling your data path. So these are the control bits. We say data path, you want it to add, subtract. If it is a traffic light, you want the traffic light to turn into red or green or blue. So you are actually sending signals and controlling something. Okay, if it's an industrial control, so actually you are saying, okay, now shut down this plant, or now this oxygen level has to be increased, or so all these are depends that in which application you are in. They may actually be controlling some physical assets in your industry, and that also is implemented as a state machine, and it can be a programmable state machine. But it is important to remember what you have said. For example, even it's a traffic light, you have said red, now you want to go to green, but you have to go to yellow and then green. Right? So that means that state is important, that in which state you are, and that will decide based on the input and the current state what should be your next state. Next state becomes the current state. So state machine are the designs where you need to know the status of the circuit of the system at a particular instance in time, because that will decide what is to be done next. Okay. For example, we did a very simple example of a state machine which counts occurrence of 4 ones. So you are sitting on a serial interface, which is just 1-bit interface, and you are getting a bit. So this is our design, and you are saying just keep noticing once you see 4 ones, you assert a 1 here. This is a simple design. So you start counting. So your first state is 0 0, and you are getting zeros. If you are getting zeros, you remain in this state. When you get a 1, so you still, because this is the first one that you have gotten, so still you generate 0 at the output, but change your state, so that now you know, your circuit knows that you have already counted 1 1 on a serial interface. And again, if you're getting zeros, you remain in this state. But once you get a 1, you now come to another state. Now you have counted 2 ones, then another 1, you have counted 3 ones, another 1, and only then you are going to generate a 1. And you say, it is good, but let's say I want to change it. If I have like 3 ones or 5 ones or 6 ones or something, you want a generic system. So you convert it into a microprogram state machine. And just a microprogram state machine is, this is your address. 0 0 is part of your state register, and 0 is part of the input. So these 3 bits will have your address. Okay, so means there is a 3 bits, so mean the memory has to be 8 deep, 2 raised to the power 3, because it depends that how many address bits you have. You need to, that will basically dictate the size of the program memory. That's why it is the program counter register size that will dictate how big a program memory you can address. So your program, the size of the program will depends upon size of your program counter register. If it is 16-bit, so your program memory cannot be bigger than 2 raised to the power 16. Okay, 2 raised to the power 16 is the size. You cannot go, and that's how you figure out that how big a program memory you can have. So 0 0, you know, this is part, 2 bits are part of the next state, and 1 bit is part of the output that you are sending to out. Maybe after counting 1 1 1, you want to lit an LED, for example. You want to open a door or what, something, anything that you are controlling. So that bit goes to the simple data path that you are controlling, and this is for you to remember that in which state your system is. This becomes your next state. So if it is 0 0, input is 0, your output is 0 0, and your output is 0. So you remain in this state. So again, your address is 0 0 0 0 0 0, and now you get a 1. Now you get a 1, automatically the address will change. You come here, and now your next state will be 0 1. Okay, so next state is 0 1 0 1. You are getting 0 0 0 0. You remain here. As you keep getting 1 1 and 1, and you have different content of the memory which are basically storing your next state, which is, again, if you have counted 4 ones, you go back and start 0 0, and 1 is the output. Okay, 1 is the output, so you get 1. So that is how you primarily run your microprogram state machine implementation. Change it into, so any state machine can be converted into a microprogram based state machine. That is important. So it's up to you whether you want to design it as a state machine using case statements, if else, or simply you want to say, here is the program memory, and you have to just figure out that what will go by just going through all the states of your state machines, and you say, I'm going to implement it as this. And it is mealy and more both, because here you will have next state and input will only define what is the next state, and this state will also tell you the output. But usually mealy machines are used to have a programmable state machine. Actually, in many hardware designs, usually you just follow a sequence. First it is you do this, then you generate this, then you generate this, then you generate this. Like we were thinking about the sorting. It says first read one operand, then read another operand, then do the comparison, then go write back, then again write back both values, then read the next operand. So it's very defined sequence of operation that you have to do. Means you may not want to save also the next state in your programming. You're wasting a lot of area. If like in a computer, if you have to keep the next state, which is only always going to be the address of the next instruction, so that will you will end up wasting a lot of space, which you are doing again and again and again, right? Wasting a lot of space. So say, why should I do that? My program is going to run in a sequence. Why should not I have a counter? Okay, and all my control signals that I have to generate in a sequence, I'll put in the program. Okay, so next state, if you are sure that next state is always going to be +1, next, because for example, here is one full adder used to add n-bit number. A sequence that first you shift this, add, do this, shift, add. So you're just going to follow sequence for 16 cycles. So there is no point for you to save the next state in your program memory. So you have a counter. Once you say reset start, I'll just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and all the control signals you store in your program memory. All the control signals you store in your program memory, and now everything is going to the data path. So reset, grrr, will start and it'll end, and you do what you want to do because you know in most of the design the sequence of control signals that you have to do, that they run in a sequence always, that you do, especially once we are doing time shared architecture. For example, sorting, you are doing a time shared architecture. You know, whenever I say sort, it is going to generate those control signals in a sequence. Right? Why should I make it very, very complicated by putting it in a very complex state machine where I know next state is always going to be the next control signal? So I should only focus on these are the way I'm going to generate control signals in 16 cycles if my design is going to take 16 cycles to do this. So it becomes the simplest microprogram state machine, which is a counter, and you do this. Like here, I'm multiplying using 1 bit. So I'll not get into the design, but many designs here. I'm going to do filters, a convolutional. We will do this in convolutional neural network as well. So you have all these registers which are updating the data. You have all the coefficients of the mask that you have, and you multiply. And remember here, as what I told you, you generate partial product and put them in sum and carry. Don't put a carry propagate adder and keep them into sum and carry while you are computing the convolution. And only once you are done with the entire thing and now you want to have one value, then you use carry propagate adder. So this is a design which also shows you how good a carry save adder technique can be used. But important is that a counter which is generating all the control signals. So the simplest is that all the control signals, let's say there are 5 muxes that you are controlling. Okay, so this is mux number 1, mux number 2, mux number 3, mux number 4, mux number 5, and let's say there are 3 enable signals that you have, or 4 enable signals that you have. Sometimes you are going to enable this register, mux should select this, mux should select this, and then you have something you are doing in 7 cycle or 8 cycle. Right? So you just start this register and it will generate all these control signals, and all these control signal will go to the directly data path, because they are basically controlling the muxes and the enable signals, and now they all are stored in memory. You're not really worried about anything. This is a sequence I'm going to execute and I'm done, right? So this is very, very good. But now you say, though I am always going to do this, but sometimes I may want it to just jump somewhere. I'll go to statement, like say I'm doing this, and here I say go and execute that part of the code. Okay. So now you say if I want this capability, and I'm going to say, okay, this is the data path, so you are going, and here you want to say you go and execute this. This is a capability you want to add in your microprogram, microcode state machine. Now you have to add more bits into the program memory, unfortunately. One is that you have to have a load bit, which is saying don't load the counter with any other value, just keep on doing what you are doing. But now you want the counter to load a branch address where you want it to go. Okay, so whenever, let's say here you want it to go, so you assert here write 1, and here you will write the address where you want it to jump, 1 1 1 0 1 and 1. Okay, so it would not care about, and you can reuse sometime these bits. So whenever this bit is 1, it means all these bits are not going to the data path, but they are the address of the next instruction. So this will assert 1 here, and counter will not take the next value. It is a loadable counter, so it will load the value which is here. Whenever you assert load, counter will jump and have this value which is part of your instruction. So this is called, now you have added a counter based unconditional branching capability into your design. Okay, so the another modification is that you say I want it to check a condition, and if the condition is true, only then it should jump. Like we do if in programming, you say if a condition, something is equal 0, only then you say go to here. Otherwise, keep executing what you are executing, right? And you want this capability into your microcoded state machine. Obviously, you have to put those conditions. Usually these conditions will come from the data path, that you add numbers and say if they are, for example, in comparator we are saying if A is greater than B. Okay, so the data path will actually subtract A minus B and see if the answer is positive. If answer is positive, it means yes, it is greater, then you are going to swap numbers. Okay, so you check condition and you say load select, check this specific condition. If your answer is positive, so here is positive, only then load the branch address. If your condition, so this is not directly going to the load pin of the counter, it is rather this is only going to a multiplexer, and where you have an unconditional, and whenever it is 0, you are not loading anything, it is always 0. So you're not loading, counter is running 0 1 2 3 4 5 6, means this bit of all the instructions in the program memory will be 0. This 0 means that this mux is going to select 0, so it's not loading anything, just running normally. Now you want to just say to blindly jump somewhere. Okay, so now you have to put here, so there are 2 bits 0 0, you have to put what, 1 1. Once you put 1 1, this mux will select this one, so it is an unconditional jump. Whenever it comes, so whatever comes here which is in the branch address, it will load and counter will start going from there. But now you want to check whether answer is positive or not, for example. So this condition 0 would be the positive flag, that if you have done some computation in your data path, answer is positive, then you want to load, and you say now you swap or you just do whatever you were doing. So this capability will add in your microcoded state. Slowly we are going to make a processor, okay, which is a programmable processor, which has subroutine calls, which can do go to statement, which can, so slowly a microprogram state machine, which we started from something very simple, then we say counter based, then we said go to, now we are saying if condition is true, only then jump, otherwise don't jump, keep executing what you are executing. So this will add that capability. So 2 bits, if you're saying if R1 is greater than R2, then jump label 3. This is a typical instruction which you will support, your architecture will support, and this is happening in your data path. And if they're positive, then you jump, otherwise you don't. Or you say if R1 equal R2, So it means you subtract and answer is 0. So you also have a 0 flag. So you are going to have 2 flags which will define this, or jump label, or just keep doing what you are doing. So there are 4 possibilities that your state machine can do. This is 0 0 means never jump, condition 0 then jump, condition 1 then jump, or always, if it is true, always jump. It is the go to statement. So and now it is getting in shape. Why to put a counter? Why not to put a program counter register which adds 1 always? Okay, program counter register, what it does is it always add plus 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 plus. It's keep on adding 1, except once you have something. So except once you have a condition, and that condition would have not address coming from the program counter register, rather the branch address which you have given here. This is very interesting. Now you say, okay, it starts from 0, so it goes to 1, then it goes to 2 instruction store, and let's say it is here, it is instruction number 11. Instruction number 11 is a conditional instruction. It says go to 100. Okay? So if it is go to 100, here you are going to write 1 1 1, and here you are going to give an address 100, and these bits you don't care, because it's not going to do anything. We're just going to address 100. So these 1 1 comes here. It says is put 1 here. So 1 is here. When 1 is here, the mux will select whatever is here, which is 100. So in the micro program, you have address 1 1, and but this on this line you have address 1 1 and 0. So the next, this will select 1, address will be 1 1 and 0, and next time, because you add 1 and it'll start doing 112 113 114 115 automatically. The program counter register will get updated automatically, and it will just start counting from where it has now jumped. So this is a register based controller, which is more like a programmable processor. This is more like a program memory. This is more like an instruction register which gets decoded in a single cycle. That's what this instruction wants to do. It's a go to instruction, wants to jump somewhere else. Okay, so slowly we are converting it into a processor. Okay, so converting it into a processor, rest of the instructions are there, and then there is a parity. You say if greater than, if not equal to, for example. So if not equal to, you set the parity bit that it should check not equal to. If it is not 0, so 0 not 0. So you have a parity bit, so you can add a parity bit as well, which can invert the condition. So if you look at a complete processor, it will look like this. Okay, all the processors would look like this. So it means that you can design a processor yourself. It has address, it has registers, many registers where you load operands, and it is basically an ALU which can do addition, subtraction, multiplications. Okay, and then it definitely it sometimes you may have a memory as well. If like only you are working on the operand, then it is fine. So you load value from memory into registers, and you write back the answer also in the memory. Right? So, but this is primarily whatever you do here. You have a, this is called the processor status register. Every processor has a status register which will say if the previous computation has resulted into an answer which is 0, it will set this flag. If the previous computation has resulted into an answer which is negative, it will set this flag, an overflow flag, a positive flag, a negative flag, a 0 flag. So processor status register has bits which are specific to status of the previous instruction that it has just executed, and they can be used as a conditional bits. Okay, to decide what processor should do if you want to. And so now instruction becoming more messy. Okay, the processor is also attached, because a micro coded state machine usually is controlling a processor through an instruction register, which would be decoded to find out what an instruction is supposed to do. Right? So this is a processor, and where you have a program counter register, this register, and then you have a parity bit, and this usually mux is called the next address mux. Should it get an address from a normal flow? If there is let's say interrupt service routine, okay, so it should get an address from here, or it should get an address from here, or it should get an address which is part of the instruction itself from here. So this will decide, and instruction would decide. If there is an interrupt, you say just go and execute this interrupt service routine. Okay? So your this mux will decide that out of these 4 options, and there may be many more, what should go forward as an address to the program memory, and then you start executing from there on. So it just go +1, then it start. So you are executing, and all of a sudden you start executing from here, and then you go and you keep executing. But now there is one thing which we have not seen yet, that how should I go back and start executing from where I left? A subroutine. Okay, we have not seen that. So we will shortly see that. You've seen the conditional execution. A subroutine, now what do I have to do? Now what I want is a simple capability in my microcoded state machine where I am executing, and now here I wanted to go and start executing a subroutine that I have written in this part of the memory. But once I hit the last instruction, which is return from subroutine, I want to go back from where I call the subroutine. So next instruction. Right? So this is a very important capability that we want to give to our programmable processor. It only means that once I'm going and jump into a subroutine, the program counter has address of the next instruction. Remember that there is a subroutine call. I'm not going to use the next address. Rather, I'm going to get the address which is part of the instruction. So I must save this address into a register which is called a subroutine return address register. Okay, so any subroutine call should enable this register, which is a subroutine return address register. Okay, SRA, subroutine return address. So this is how it works, that you have this this is a program counter. This is your subroutine return address register. Its enable is coming from if it is a subroutine call or not. If it is a subroutine call, we will assert one here. This address, which has the address of the next instruction, gets stored here. But what gets here is the address of the subroutine, which is coming from part of the program, which is the from where it should jump, the branch address. Okay, so this branch address would actually, which is part of the instruction, is here, and you start going here, and then once you return, it should select the next address mux should select the return address. Okay, should select the return address, and that's how you add the capability of subroutine in your micro-coded state machine based design by having. Okay, so this is one of the questions I gave it in an exam, that put all these in your data path. Then you should able to do the unconditional branching, conditional branching. So go to statement, but branch if accumulator is 0, accumulator is less than 0. Always branch, unconditional, call subroutine, return. So you can have an instruction set. Now slowly, and this is what we said, instruction set architecture. Okay, if you have an architecture which runs on an instruction set, that architecture is called, I have an instruction set architecture. It's not just a hard-coded state machine based design where I'm sharing some of the hardware so that it becomes effective. You say, I have an instruction set architecture, and this is my instruction set. Okay, so means using this instruction set, anybody can write any program, definitely, which is in the capability of the instruction set. So you say CISC, complex instruction set architecture. CISC is a complex instruction set architecture where an instruction can do very, very complex things, single instruction. But usually people have been preferring RISC, which is reduced instruction set architecture, where there are very few instructions and they're very simple instruction. So if you want to do a complex thing, instead of adding a complex instruction in the instruction set, you break it down into reduced instructions so that you are very fast. And because you are fast and this is very slow, you are adding a complex instruction which you may never use in your program. For example, you have an instruction which can generate cosine. A very complex instruction, you give theta, will generate cosine. Here there is an instruction, and for that you have made your instruction set so complex, your decoder so complex. And in many programs, you're not even using that instruction. The people started thinking about why to go for a CISC architecture. Why not to have a very simple architecture which can just do addition, subtraction, multiplication, this, that, always register based. And if I have to do a cosine, which perhaps I'll do once in a moonlight, okay, I will do once in 1,000,000,000 times. So I'll break it down into a simple instruction and I'll execute it. Okay. So all general purpose processor would prefer not to be CISC, not to be a complex instruction set architecture. But if you have like a very specific architecture which is supposed to do a very specific task, okay? For example, and they started doing digital signal processor because they know all the time they're doing MAC. So very complex instructions where they can do 8 MACs in a cycle, 8 multiplication accumulation operation in single cycle. Very complex instruction, right? Very complex instruction. Now there are even 16 multiply accumulation happening in a single cycle because it's an application specific instruction set computer. And sometimes they do a VL, very large instruction word architecture, where you have your instruction is controlling many data paths. So many adders, so many multipliers. So every part of the instruction is controlling a part of the data path, and you make a VLIW architecture, very large instruction word. Okay. So instruction set architectures are very interesting architecture because they give the user an ability to write a program, change the program, have the capability to, if it is very general purpose like Pentium or MIPS or RISC or ARM, or so they are very general purpose. So they are designed keeping no application in mind because they are supposed to do almost anything. But if you look at GPUs, they are designed to have a very specific purpose in life, that this is what they are going to, a graphical processor, a very specific thing that it is going to do. Same is the case with digital signal processors, very specific application in mind. Video signal processor, encryption processor, this processor, that processor. So, you once you are designing your instruction set, this is where the main thing is how good an instruction set you design for a specific application. Okay? And because it's an instruction set, you should try the instructions that can be used repeatedly. Don't try even in that making an instruction which is a very complex instruction for nothing. And then you are adding a lot of space in your instruction set, then a lot of space in your hardware. Try to break down the concept of complex instruction set and reduced instruction set are even going to be there even if you are designing an application specific processor. Try the instructions even for that specific application that will be used repetitively. You say, I have an instruction set architecture and it has the capability to even do complex things, but I have designed it in a manner that most of the instructions, most of the data paths will be used all the time. Right? So that's what. So a lot of analysis that you have to do once you are designing an instruction set for an architecture. Now, sometimes you may want to sports nested subroutine. What is nested subroutine? You go and you call a subroutine, so you go and you start executing this subroutine. This subroutine then goes and call another subroutine. This subroutine then goes and call another subroutine. And this subroutine then goes and call another subroutine. Okay? So in a function, you go to another function, in that one you go to another function, and now you have to come back. Once you say return subroutine, you must come back here. Once it says return subroutine, you must come back here. Once you say return subroutine, you must come back here. Once you say return subroutine, then you come back to here and start executing again. So nested subroutine support sometimes is also very important. That how do you give a nested subroutine support to your architecture, and all you have to do is now your program counter register, once you are saving in a return address, will become a stack. You push it on a stack, LIFO, last in first out. So the address of the next instruction goes there. Then you go another call another subroutine. Again, that address will go into that LIFO. So if you want to give this port 4 times, remember we did this LIFO and FIFO. They're so important that now if they are full, they are empty, and you're just saying return where there is nothing. You have never jumped, or you are saying subroutine, 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 subroutine. You are pushing the 5th value. It must generate an error, so that the user must know that you have not called for you have already called 4 subroutine, and it does not support the 5th subroutine call. Okay, so LIFO is where, or so this is a typical LIFO. So you have first address comes here, then you push it, go back here, then you push it, goes back here, then you push it, goes back here, and whatever is top of the stack, you say this is return, and then it is coming back here like this. So if you return, then again you have to update this. So there is an address here. So this is the older one, this is the newer one. So you push this out, and once you push this out, you bring this value here as well. So LIFO is running all the time. So this is the only thing that you need to do, that if you have a nested subroutine call, you make a stack which is a LIFO. Okay, so LIFO has top of the stack pointer. This is the top of the stack pointer, which will say what part. It's just a LIFO, which we have already done. So just instantiate a LIFO here. Similarly, you may want to have a loop support. Sometimes you want to repeat a set of instruction. Okay, this is, you don't want, this is not a subroutine. You say repeat this piece of code 1000 times, 100 times. This is a very typical for loop instruction. That for loop instruction is an instruction where you want your processor to repeat a set of instruction a number of times, and you want to give the support to your instruction set architecture. So it is typically, you are here, you say repeat 20 times till 100. So you have to give an end address. Okay, so this end address is here. Automatically, once you hit this repeat instruction, program counter has the start of the loop. It has the next instruction in it. So this is the next instruction, address of the next instruction. And here is the counter. So you got to save in a repeat instruction 3 values. One is how many times you want to repeat, what is the start address of the loop, and what is the end address of the loop. So always comparing a program counter with the end address. Whenever you hit end address, you check counter is not 0, you go back and repeat, you go back and repeat. So this is called zero overhead looping, that you have a loop machine to support single loop instructions. So you have the loop counter register, you have the loop end address and loop start address. Okay, and there is a logic which is ensuring that you can kind of all the time. And interestingly, what if you have nested loop? In a loop, you have another loop. In that loop, you have another loop. In that loop, you have another loop. That is something you do a lot once you have a computationally intensive algorithms, linear algebra, neural networks, CNN, and you want to give this support. If you want to give this support to your machine, all these registers will become stacked, 4 nested subroutines. So you have to store 4 counter values, you have to store 4 start address, 4 end addresses, and there will always be something which is on top of the stack. The loop which is executing gets, the counter has to be decremented. So you have like loop counter for loop end address 4. So this is the innermost loop, and so it until it expires, it keeps on doing here, and only then it goes back and start executing the outer loop. And until this expires, it just keeps moving. And so this thing gets executed many number of times, because again you are going to hit a repeat instruction. So you are executing this, you go back this, and then again you will hit this. So the innermost loop gets, then you are doing this, again you do this, and once you are doing this, again you do this, and you go back this. So very nicely you can have a loop machine which can support as many nested loop as you want. If you want 4, it'll support 4. And remember, it's a LIFO. If you try to put another loop, it'll generate an error that you cannot do this. So you must have an exception coming out of your architecture saying you are trying to call a loop machine more times than it is capable of doing. So either you have more support here for 8 nested loop support, or you cannot actually use this loop machine to support. So this is actually, these drawings are coming from an actual architecture that we did, a processor that we did, which supported 4 nested loop. So this drawing is actually from there. Okay, so you may have now an architecture which has an instruction set which can support nested subroutine calls, which can support nested loops. So all this is possible, that you have now a processor which has an ALU, which has a register file, which has a memory, which has so you can have a complete architectural drawing at architectural level. I have been giving these questions in the exams to have this support in your data path, and then you may want to have a call subroutine support, a return to subroutine support, and for loop repeat support, and it depends like how much you intend. So there is a paper which talks about all these things. This is implementation of microprogram controller in FPGA, and interestingly, it is controlling a plant, a physical plant. So you can actually, your microcoded state machine can control a physical plant. Check this, do this. Now, if you're shutting down, there is a subroutine that how you are going to shut down a part of the plant. And so it almost, in this paper, almost the same thing is kind of repeated. There you have a program counter register. It gets incremented by 1. And there is a next address register, which can either get the address from the program counter register or a branch address, which is going into this next address mux. There is a parity bit, and these are the conditions. There may be many conditions that you have. Based on that, you decide what should be the next address. And so here is the microprogram memory. The instruction comes in this register, which is the instruction register. And this would then gets decided that what next you want to do. So there are outputs which are going to control the plant. And then, so you can have a generic FPGA based design. You say, I have all these capabilities, and I have n bits for you to control physical devices. So you just write your program, a plant control based FPGA, where you have many wires, which you say you can control different machines. Write a program what you want to do. The program has the capability to call subroutines, to do for loop, to have instructions which are used to control different things in this. And these conditions may be coming from the plant. If there is a specific machine which has which temperature has gone beyond the limit, or there is a breakdown of something, or some gases are being emitted which are being sensed, So all these conditions are coming from a physical plant, and based on these conditions, you do something. So, oh, here is a condition, I need to do this. I need to increase the oxygen level, I need to reduce this. So, very interesting aspect of a plant control, where you have an instruction set, FPGA-based implementation, which is very generic. Okay, you're given enough bits for it to control different machines in the plant, and write any program of your choice which supports conditional subroutine calls, go to statements, this and that. So then it talks about the loop machine as well. The nested subroutine, which needs to have a LIFO. Loop counter, you need to have a LIFO. Right? So once you are implementing, so the next address selection gets messier, because now it is end of the loop, start of the loop. So you need to provide that also. If subroutine, return address, normal, interrupts. So you don't mind, because you are just designing a generic processor which could any plant can use. Any plant can use for the control of the plant. So these are also some of the questions from the exams that I've been taking of this subject, and also you will find them in my book, that design this 2 deep subroutine call, nested subloop. So it depends that, but important is that you can design any instruction set architecture which specific to the data path, which may be a convolutional neural network, which may be a physical plant, which may be a communication algorithm, which may be an encryption algorithm, which may be anything. Right? So if you can convert the sequence in which something has to be executed into a microprogram, into instructions, then you can have your own instruction set processor. And that instruction set processor is good because you can convert the algorithm into instructions using your instruction set, all these capabilities. And controller is basically you provide all the support, and all the support is very generic. Subroutine calls and the loop machines, they are very generic to any processor. I think let's take a break, and हम break कर लेते हैं.
Sir, I
जी
have a
कोई
question.
question?
Sir, I have a question.
जी जी.
Sir, we have seen like we are designing this micro program state machine design, but how do we actually translate our program into the micro program memory? Do we do this by hand, or are there some tools for it? Because in the controller-based design using the FSMs, the design grew very large, and it was very difficult to basically manage the design using the FSM.
Yeah, it is. It depends upon the complexity of the problem. One way is that you do it by hand. The other one is you design an assembler, which will you write mnemonics for every instruction, like R0 is equal to R5 plus R6, and then you have an assembler which will convert these, parse it, convert it into the bits, because the program memory you have to fill in the bits. And then you can even have a linker, loader, assembler, compilers, so that's how the whole thing it grows. Initially you can write it in machine language, where it's a small problem, you say, why should I go and write an assembler for this? So you write it yourself. There are, let's say, total of 100 200 instructions. You say, I can very well just write it manually. But then you say, no, because I am just providing this an algorithmic state machine based processor, and I'm claiming that users can reprogram it. So then you say, I will also provide you with the tools. So once we started designing this, we first developed these assembler, loader, linker, and started becoming very complex once, because start going towards more generic processors, then the tools becomes very difficult to design, because writing a compiler is not that simple, because converting a high level language into instruction set is very difficult. So it's again depending upon the size of the problem. What we are learning in this course is just manual is good enough, that you just look at the instruction and do it manually. But if you are doing some professional job, developing a CNN architecture, a programmable convolutional neural network architecture, and then and you are just selling it as a instruction set architecture, then you have to develop the tools as well.
So for more generic problems, we go a high level of extraction and rely
Yes,
on compilers and linkers
yes,
and loaders.
yes, yes.
Okay, sir. Okay, sir. Thank you.
थैंक यू। ठीक है जी, तो इंशाल्लाह हम मिलते हैं 30 मिनट्स में।